Hello everyone, the topic of my speech is resource optimization of power line communication network based on Monte Carlo method. Next, I will give my speech in 5 parts. They are introduction, system model, system performance optimization based on Monte Carlo algorithm, simulation and result analysis and conclusions. First, introduction. The widespread use of power line communication networks and distribution lines makes PLC become an excellent choice for industrial command and control and facility automation systems. Based on the existing research background, the main contribution of this paper is: firstly, we analyze the main factors that cause packet loss based on the fading and noise of the power line physical layer and the CSMA background mechanism of the MAC layer. Secondly, we establish a system throughput calculation model based on the packet loss factors. Finally, according to the Monte Carlo algorithm, the MAC layer contention window selection algorithm is established based on the principle of maximum throughput. Compared with the original algorithm standard, the effectiveness of the method is verified through the simulation results. Secondly, system model. As for the MAC layer, briefly, the implementation of the CSMA background algorithm uses the following 3 counters. Backoff procedure counters indicates the number of backoff stages. Backoff counter indicates the random backoff time. Deferred counter is used to evaluate the business of the current channel. Moreover, it also makes the station react to the high load in the network without the collision. As for the physical layer, we assume a single hop transmission model and consider log-normal fading and impulse noise in the channel. We assume that S is the source node and D is the destination node. Then the signal received as D can be expressed as, and the corresponding noise probability density function can be expressed as. Based on the MAC layer model, if 2 or more packets are sent at the same time, the packet will be collided, causing the failure of transmission. As for physical layer, if the signal-to-noise ratio of the transmitted signal is less than the threshold, the transmission will be interrupted, which will also cause the failure of transmission. These 2 transmission failure situations will affect the performance of the system, especially the factors of the fading parameter in physical layer and the value of contention window in MAC layer. The outage probability of the channel can be characterized as. The collision probability model can be expressed as. It can be seen that when more than one station send packets at the same time, it will cause packet loss. While considering physical layer, the overall packet loss probability can be characterized as. Thirdly, system performance optimization based on Monte Carlo analog. Thirdly, system performance optimization based on Monte Carlo analog. The Monte Carlo method is a type of machine learning algorithm In this Monte Carlo method, we set the size of the cycle package to 10 to the 6. The meaning of this value is the number of successfully transmitted packets in each round of the loop. We let a certain number of stations experience the backdrop of CSMA, and we set the initial value of the minimal backdrop window to 4, and each station performs the independent backdrop process. In this process, if the backdrop contention window of X stations are reduced to 0, these stations will be sent, and if X is greater than 1, these packets will be collided. If the transmission force, the number of failures will be counted. And if X is equal to 1, the station will be transmitted in the channel. But due to the possible poor channel conditions, the transmitted packet is affected by log-normal fading and noise. For X is equal to 1 in each cycle, we generate a random number that obeys log-normal fading under the certain variance, and generated the noise concerning binary Gaussian process. According to these two parameters and the transmission power, the signal-to-noise ratio expression is constructed, and it will be compared with the threshold. If the signal-to-noise ratio of the signal is lower than the threshold, the channel will be interrupted and the packet transmission force. Otherwise, the packet will be transmitted successfully, and the success and fault will be counted according to the success or failure of the transmission. After 10 to the 6 packets are successfully transmitted, the throughput of the system is calculated and the contention window value is recorded. When the value of the contention window is doubled, the process of the right side of the diagram is repeated again. If the throughput corresponding to the contention window value is lower than the previous value, the experiment is terminated, and the corresponding contention window value and the throughput are recorded. The basis for this is that with the increase of the contention window value, the throughput can only have the two trends. First, keep decreasing. Second, first increase and then decrease. Based on this experiment, the contention window value corresponding to the highest throughput under the certain number of stations can be obtained, because for the certain number of sending stations, a lower or higher contention window value may cause performance degradation. That is, there is always the most suitable contention window value. The specific Monte Carlo algorithm flowchart is shown here. Based on the theoretical framework, the normalized throughput is expressed as, where success represents the number of successfully transmitted packets, and fault represents the number of the lost packets. Next, the simulation and result analysis. This figure shows the throughput performance curve under different initial contention window value and the number of stations. It can be seen from the curve that as the number of stations increase, the corresponding throughput first increases and then decreases. Therefore, for different number of stations, there is the there is an optimal window value corresponding to the maximum throughput. We select the number of stations to participate in the Monte Carlo situation. In addition to collecting the result of the algorithm described in the section 3, we also separately simulate the throughput under the adjacent contention window to verify the effectiveness of the algorithm. It can be seen from the graph that the Monte Carlo algorithm can indeed help to find the best window value and the corresponding maximum throughput. And the window value increase, the more stations there are, the faster the throughput will increase. Moreover, as the window value continues to increase, the throughput will decrease first, and when the number of stations is small, indicating that in order to ensure the better system performance, when the number of stations is larger, it is suitable to use the larger window value. This figure shows the initial value of the contention window corresponding to the extreme point of the throughput under the number of stations from 1 to 15. It can be seen that as the number of stations increase, the corresponding optimal contention window increases. It is because as the number of stations increases, the larger contention window value can lead to the lower packet loss probability, so the corresponding throughput can be improved. Because in the algorithm, we increase the contention window by a multiple of 2, the fewer of the number of stations, the more obvious the change in the contention window value of the corresponding to the best system performance. The result in the figure is not only the result of the number of stations, but also the result of the combined effect of the CSMA background mechanism and the physical layer parameters. This figure shows the performance result based on the CSMA protocol standard and the curve comparison chart of the throughput corresponding to the optimal contention window value under different fading coefficient obtained based on the Monte Carlo algorithm. As shown in the figure, the contention window value found by the Monte Carlo algorithm is actually the optimal solution, and its performance is better than that of the calculation. And the smaller the channel fading coefficient is, the more obvious this advantage is. This is because when the channel fading coefficient is smaller, the signal to the noise ratio is larger at this time. So the outage probability of a system is smaller, resulting in a smaller system packet loss probability and the higher throughput. Therefore, if the channel fading becomes severe, the system performance will have a negative impact. But even so, the Monte Carlo algorithm is still better than the original standard performance. To a certain extent, this algorithm can not only improve the system performance, but also in the face of unpredictable and inevitable fading in the channel, the system performance will not be affected too much. This figure shows the performance result based on the CSMA protocol standard and the curve comparison chart of the throughput corresponding to the optimal contention window value under different impulse noise occurrence probabilities based on the Monte Carlo algorithm. It can be seen that Monte Carlo algorithm finds the performance of obtained contention window value is obviously better than the performance corresponding to the contention window in 816 13 to 16.4 in the IEEE 1901 protocol standard. Regardless of the probability of the impulse noise, the performance of these two algorithms does not change significantly. This is because under a certain signal-to-noise ratio, even if the probability of impulse noise is changed, the noise power is actually not affected so much that the impact on the signal to the noise ratio is not obvious. Therefore, compared with fading noise, has a not obvious impact on the system performance. Lastly, conclusion. This paper uses a Monte Carlo algorithm to optimize the performance of the power line system, considering the log-normal fading in the channel, impulse noise, and the background mechanism in the MAC layer. The corresponding physical layer MAC layer throughput performance is analyzed. Furthermore, how to obtain the contention window value under the optimal performance through the Monte Carlo algorithm is studied. The results show that based on the Monte Carlo optimization algorithm, the optimal contention window value under the corresponding number of stations can be obtained. And for the low fading environment, the degree of the optimization is particularly obvious, thereby optimizing the network resources of the power line communication. Thank you for your listening.